History and background of R is a language and environment for statistical computing and graphics. It has its roots in the S language and environment, which was developed at Bell Laboratories. R was created by Ross Ihaka and Robert Gentleman at the University of Auckland, New Zealand, and is currently developed by the R core team. The command version displays information about the current version of R, including its origins and some historical details. This illustrates the ongoing development and history encapsulated in every release of R. Installation and setting up the R environment. Before using R, you need to install it. R can be downloaded from the Comprehensive R Archive Network, CRAN. To install R, first visit the CRAN website at hts://cran.rproject.org. Choose the version appropriate for your operating system, Windows, Mac OS, or Linux. Download and run the installer, following the on-screen instructions. No specific code is needed for the installation process itself, as it is a typical point-and-click installation. RStudio Overview. RStudio is an integrated development environment, IDE for R. It provides a user-friendly interface for writing and executing R code. The interface typically consists of several panes, including a source editor, console, environment, history, files, plots, packages, and help. This overview doesn't require a code block, as it's a general introduction to RStudio's layout and capabilities. RStudio simplifies the process of writing R code, managing files, visualizing data, and more by segmenting these tasks into different panes within the IDE. For instance, you will write scripts in the source pane, see real-time output in the console pane, manage workspace variables in the environment pane, and view generated plots in the plots pane. Basic syntax. R is a scripting language, meaning that it executes commands as they are written in a script. Here we'll see how to write a simple R script and execute basic commands. We start by creating a variable x and assigning it the value 42, using the assignment operator manus. We then use print to display the value of x. After that, we perform a basic arithmetic operation by adding 58 to our variable x and storing the result in a new variable sum. Finally, we print sum to see the result of our addition, which outputs the total value. Variable types and data structures. In R, variables can store data of different types. The basic data types in R include numeric, integer, complex, logical, and character. The code snippet assigns different types of values to variables, is assigned a numeric value, B an integer indicated by L, C a complex number, real plus imaginary, D a logical value, true false, and E a character string. Packages and libraries. Packages in R are collections of functions, data, and compiled code that are bundled together. After installing a package, it must be loaded into the session to use it, which is done with the library function. The first line of the code installs the ggplot2 package from the Comprehensive R Archive Network, CRAN. The second line loads the ggplot2 package into the current R session, making its functionality available. This is necessary because installing a package is a one-time action, but loading it with library is required every time you start a new R session and want to use that package. Getting help and documentation. When using R, it's common to need help understanding functions, finding the correct syntax, or exploring the uses of different packages. R provides built-in help features accessible directly from the console. The question mark E, followed by a function name, e.g. dat_mean, opens the documentation for that specific function. If you are unsure about which function to use, or want to search for topics related to a term, you can use the double question mark, followed by a term, e.g. regression. This will search the help system for relevant functions and documentation related to regression. Arithmetic operations. In R, you can perform standard arithmetic operations such as addition, subtraction, multiplication, division, exponentiation, and modulus. These operations work on atomic vectors like individual numbers, as well as on more complex objects such as arrays, matrices, and data frames under certain conditions. The code performs basic arithmetic operations using two variables, a and b. We define a as 25 and b as 5. Then we proceed with addition, a plus b, subtraction a minus b, multiplication ab, division ab, exponentiation a raised to the power of b, and modulus operation, remainder of a divided by b. The results are stored in variables named after the operation. This demonstrates how basic math operations are executed in R. Logical operators. Logical operators are used in R to compare values and result in either true or false. The main logical operators are and, or, not, equal to, each equals not equals than, less than, greater than, less than or equal to, and equals, greater than or equal to. These operators can be used to perform element-wise comparisons between vectors, or to check conditions in control flow statements like if-else and loops. In our code example, x is assigned the value of 8, and y is assigned the value of 50. The result variable will get the outcome of the logical comparison, x was 10 and y 100. The operator an checks if both conditions, x 10 and y 100, are true. Since x is indeed less than 10 and y is less than 100, result will be set to true. Assignment operators. In R, assignment operators are used to assign values to variables. The most common assignment operators are s less than followed by a hyphen, which is used in scripts, and calcs, which is more commonly used in functions and in console. There is also lat minus, which assigns a value to a variable in the global environment, not frequently used, and should be handled with care. In the code provided, x is assigned the value 10 using the minus operator, y is assigned the value 20 using the equals operator, and z is assigned the value 30 using the that operator. Each of these operators is effectively doing the same thing. They are storing a value inside a variable. However, the context in which they are typically used varies, and the things operator has a broader scope, potentially affecting the global environment, which can lead to side effects if not used carefully. Comparison operators. In R, comparison operators are used to compare two values or variables. The result of a comparison is a logical value, either true or false. The code provided demonstrates the 6 basic comparison operators in R. Each line compares two numerical values using a different operator. The first line checks if 5 is less than 6, which is true. The second line checks if 5 is greater than 6, which is false. The third line checks if 5 is less than or equal to 5, which is true. The fourth line checks if 5 is greater than or equal to 6, which is false. The fifth line checks for equality between 5 and 5, which is true. The last line checks if 5 is not equal to 6, which is true. Built-in functions. R comes with a host of built-in functions that provide basic functionality for mathematical calculations, statistical analysis, sequence generation, and more. Here we see 4 examples of built-in functions in R. Sum 1 to 10 calculates the sum of numbers from 1 to 10. Mean C1 4 7 2 computes the average of the given numbers. Security 16 finds the square root of 16. Length C apple, banana, cherry determines the number of elements in the vector composed of fruit names. Vectorization. Vectorization in R refers to the ability of a function to operate on an entire vector of values at once, rather than requiring an explicit loop to iterate over each element. This leads to more concise and faster code, as vectorized operations are typically implemented in optimized C code under the hood. Let's look at a simple example where we add 2 vectors element-wise using vectorized operations. In this example, A and B are 2 vectors containing 5 elements each. The plus operator is vectorized in R, meaning it automatically applies the addition operation across corresponding elements of A and B. The result is a new vector, vector sum, containing the element-wise sums of A and B, without needing to use a loop. The output will be vector sum containing the values 6, 6, 6, 6, 6. Vectors. In R, a vector is one of the fundamental data types. It is a one-dimensional array that can hold numeric data, characters, or logical values. Vectors have to contain all elements of the same data type. If you mix types, R will coerce to the most general type. Let's create some vectors of different types and do basic operations with them. Here, C combines values into a vector. Numeric vector contains numbers, character vector contains characters, and logical vector contains logical Boolean values. Sum numeric vector holds the sum of numeric vector elements. Subsetting contains the first three elements of the character vector. Logical and vector performs an element-wise logical AND between the logical vector and another vector of Booleans. Matrices. In R, a matrix is a two-dimensional array that has rows and columns containing elements of the same data type. A matrix is created using the matrix function, which can take a vector of data as input and shape it into a matrix with a specified number of rows and columns. You can also specify whether the matrix should be filled by rows or by columns with the byrow argument. The code creates a matrix M with 3 rows and 3 columns using the numbers from 1 to 9. The matrix function is being used here, with the first argument as the data to be filled into the matrix, which is a sequence from 1 to 9. The nRow argument specifies that the matrix should have 3 rows, and the nCoal argument specifies that the matrix should have 3 columns. The byrow argument is set to true, indicating that the matrix should be filled by rows. If byrow were false, the default, the matrix would be filled by columns instead. Arrays. In R, arrays are data structures that can store data elements of the same type arranged in a multi-dimensional grid. They are similar to matrices, but can have more than 2 dimensions. The array function is used to create an array, which takes a vector of data and a dimension vector as its arguments. The code creates a 3-dimensional array named ArrayData using the array function. The data elements are the integers from 1 to 12, and the dim argument specifies the dimensions of the array, where 2 rows, 3 columns, and 2 layers are created. Lists. In R, lists are a special type of vector that can contain elements of different types. Lists are very useful in R because they can store a collection of objects, which can be of varying types and structures. A list can contain numeric values, character strings, vectors, matrices, data frames, and even other lists. In this code snippet, we created a list called myList using the list function. The list myList contains 4 elements: a character string Alice under the name name, a numeric value 25 under the name age, a numeric value 5.6 under the name height, and a sequence of integers from 1 to 10 under the name data. Each element can be accessed using the $ operator, e.g., myListDolName would return Alice. Data frames. In R, data frames are used to store tabular data. They are similar to matrices, but allow for different types of data in each column. Each column can be thought of as a vector, and they must all have the same length, although they can store different classes of data. This code creates a data frame named df with 3 columns. Column 1 contains numeric values 1 to 3. Column 2 contains the characters A, B, C, and column 3 contains Boolean values true, false, true. Each column is created by a vector of the same length, combining different types within one data frame. Factors. In R, factors are data structures used for fields that take on a limited number of different values. They are useful in statistical modeling. Factors are particularly useful when dealing with categorical data, e.g., levels of a qualitative variable such as low, medium, high. R stores the variable levels as integers under the hood for efficiency, but represents them with their associated labels when you print them out. In this example, we create a factor gender with levels male and female. We then display the levels of this factor using the levels function. The output will show that our factor gender has 2 levels, male and female. Internally, R represents these as 1 and 2, but they are displayed using their character labels. Indexing and subsetting. Indexing and subsetting allow you to extract parts of a data structure. When working with vectors in R, you can use indices to access elements using their positions. Positive integers return the elements at the specified positions, negatives omit them, and logical vectors select elements where the corresponding index is true. The first line creates a vector. The second line indexes the second element, 4. The third line uses negative indexing to omit the second element, resulting in C, 2, 6, 8, 10. The last line uses a logical condition to select even numbers, so it returns the same vector since all elements in my vector are even. Sorting. Sorting is a fundamental aspect of data manipulation in which you rearrange the elements of a vector or the rows of a data frame in a particular order. In R, this is commonly done using functions like sort, order, and arrange from the dplyr package. In the first line, sort is used to arrange the numbers in a vector in ascending order by default. The second line shows how order is employed to arrange a data frame based on a specific column. Here, $column is the column we want to sort by. The result sorted df will be a data frame sorted by that column. Merging and binding data. In R, you can combine data frames by columns with the merge function. It works similarly to SQL joins. You specify the data frames and the key columns to match. This code takes two data frames, data frame 1 and data frame 2, and merges them on a column named key column, which must be present in both data frames. The result is stored in a new data frame called merged data. If key column has matching values in both data frames, the corresponding rows are combined in the result. Aggregation. Aggregation in R is the process where data is summarized or reduced to a few descriptive statistics based on certain groupings. It is particularly useful in scenarios where one wants to compute summary statistics, such as the sum, average, or standard deviation of a particular column in a dataset grouped by one or more other columns. Base R provides functions such as aggregate, while the dplyr package offers a more intuitive syntax with functions like group by and summarize. In the code example, we are using the dplyr package's group by and summarize functions to demonstrate aggregation on a sample data frame sample df. Firstly, a sample data frame is created with a group column and a numeric value column. Then it is piped %% into group by group to indicate that subsequent operations should consider the group column. The summarize function is then used to calculate the count, mean, and sum of the value column for each unique group, A and B. The result is stored in aggregated df, a new data frame containing the aggregated statistics. Apply functions. In R, apply functions are a family of functions which allow you to perform actions repetitively across rows or columns of a matrix or data frame. The most common apply functions are apply, lapply, supply, and tapply. These functions take an input data structure and apply a function to it, simplifying the process of operations that would otherwise require explicit loops. This code calculates the mean of each row. 1 indicates rows, 2 would indicate columns, in a matrix named matrix data using the apply function. The second argument specifies the margin we're operating over, 1 for rows, 2 for columns, and the third argument is the function, mean in this case, to apply to each row column. Reshaping data. Data can be in a wide format, where each subject's attributes are spread out across columns, or in a long format, where each row is one observation. To make data analysis or visualization easier, it's sometimes necessary to reformat data from wide to long. In R, we use functions like melt from reshape2 or pivot longer from tidyr. For this example, we will convert a data frame from wide to long format using pivot longer. The code begins by loading the tidyr library, which contains the pivot longer function. A sample data frame, data wide, is created with an ID column and two time point columns, time 1 and time 2. The pivot longer function is then used to transform data wide to long data. The cols argument specifies which columns to lengthen, those starting with time. Names2 assigns the name for the new key column, and values2 names the column for the consolidated measurement values. The result is a long format data frame with ID, time, and measurement columns. Tidyverse packages for data manipulation. The select function from the dplyr package is used to choose columns in a data frame that you want to work with. You can specify columns by name, or use helpers like starts with, ends with, contains, matches, or everything to select columns based on their names. The code snippet first loads the dplyr library, then creates a data frame with 3 columns, X, Y, and Z. The The select function is then used to create a new data frame, selected data, that contains only the columns x and z. The cent% operator is a pipe that passes the left-hand side data frame to the select function on the right-hand side. Reading data from files, CSV, Excel text. CSV, comma-separated values files are a common file format for storing tabular data. R can easily read CSV files using the read.csv function. This line of code reads a CSV file from the specified path and assigns the data to the variable data. The data is read into a data frame, which is a table-like structure in R suitable for storing datasets. Writing data to files. When you've manipulated or analyzed your data in R, often you'll want to save your data for future use or to share with others. One common format for doing so is CSV, comma-separated values, which is readable by many programs, including Excel. The function write.csv is used to write a data frame or matrix to a CSV file. The first argument, my data, should be replaced with the name of your data frame or matrix. The file argument specifies the name of the file you want to save your data to. The argument row.names equals false is included to ensure that row names are not saved to the file, which is usually the desired behavior. If you want to include row names, set it to true. Working with web data and APIs. Loads data from an online source through an API using the HTTP and JSON-like packages. It sends a GET request to the specified API endpoint and processes the JSON response. The code uses the HTTP library to send an HTTP GET request to an API endpoint and then checks the response status code. If the response indicates success, code 200, it proceeds to pass the JSON content with the from.json function from the JSON-like library. The passed data is stored in the JSON data variable and printed to the console. It's essential to handle different status codes and potential errors appropriately in a real-world scenario. Database connections. In R, we can connect to databases to query, fetch, and write data. This is often done using the DBI package, which provides a common interface to relational database systems. The specific database driver, e.g. RMySQL, RSQLite, RPostgreSQL, is also required. The following example demonstrates how to connect to an SQLite database and retrieve data. We load the DBI library, establish a connection to an SQLite database using dbconnect, and specify the database file. Then, we retrieve all the records from my table using dbgetQuery. Lastly, we disconnect from the database with dbdisconnect to avoid leaving open connections. Control structures: if, if-else, for, while, repeat. The if statement in R is a fundamental control structure that allows you to execute a block of code if a certain condition is true. In the provided if statement structure, condition is a logical expression that is evaluated. If it returns true, the code inside the curly braces is executed. If condition is false, the code block is skipped. Functions. In R, functions are used to encapsulate a set of instructions that can be reused throughout a program. A function can take inputs, execute code, and return output. Defining your own functions in R can help in reducing repetitive code and makes your code cleaner and easier to understand. In the provided code, a function named add is defined with two parameters, x and y. The function calculates the sum of x and y and stores it in the variable sum. The return function is then used to explicitly return the value of sum. After the definition, the add function is called with arguments 5 and 3, and the result is stored in the variable result. Scoping rules. In R, scoping rules determine how values are associated with variables. The two main scoping rules are lexical scoping and dynamic scoping. R uses lexical scoping, which means the values of free variables are searched for in the environment in which a function was defined, not the environment from which it was called. Here's an illustrative example. In this code, when function 2 is called inside function 1, it prints the value of x. This is because x is a free variable in the global environment, which function 2 has access to. However, y is defined only in the environment of function 1 and is not accessible within function 2. Attempting to print y within function 2 would result in an error because y was not defined in that scope. Looping and conditional execution. Looping in R is used to execute the same block of code for a given number of times. Common loops include for, while, and repeat. Here we will use a for loop to iterate over a sequence of numbers. The code creates a for loop that iterates through a sequence of numbers from 1 to 5. In each iteration, the current value of I is printed to the console. The loop stops after completing the last iteration when I equals 5. Debugging and error handling. In programming, bugs are inevitable. Debugging is the process of finding and resolving errors or bugs in a program. In R, errors may come in various forms, such as syntax errors or runtime errors. Proper error handling ensures that your program can deal with unexpected inputs or situations gracefully without crashing. The code defines a function, error handling function, that calculates the square root of a given input x. Before attempting the calculation, it checks whether the input is numeric using the is.numeric function. If the input is not numeric, the function stops execution and throws an error with the message, input must be numeric, using the stop function. If a non-numeric value like a string is passed to the function, an error is raised, demonstrating a simple form of error handling.